Now let's consider a tertiary alkyl halide, and we know that tertiary alkyl halide undergo nucleophilic substitution reaction via a SN1 mechanism, right? So we know this, and here we are taking a chiral molecule because this carbon, which is colored in cyan, is attached to this molecule, which is colored in cyan, is attached to four different groups: a ethyl group, a methyl group, an isopropyl group, and a bromine. So it's a tertiary alkyl halide containing a chiral center, and we know that this bond, so this bond between the carbon and halogen, so this bond between the carbon and the halogen, if it is broken, you get a tertiary carbocation. Now, if we visualize this molecule, it really looks very clumsy. So here it's the same molecule where you have to this carbon. So with this is the chiral carbon. So this carbon, you have an ethyl group, you have a methyl group, and then you also have a isopropyl group attached. So that's your isopropyl group. So that's your isopropyl group. Since this looks really clumsy, we will just consider three different groups that are attached to C1 as R1, R2, R3, and then bromine will take it as Br. Now, what we have done here is that we have taken the same molecule, but we are representing it in a less easy to view kind of representation, where you have this, which is C star or C asterisk, which is the chiral carbon, to which three different R groups are attached: R1, R2, R3, and you also have the halogen, which is bromine, attached to the carbon. So the first step in an SN1 reaction is the cleavage of the carbon halogen bond. So let's say that your halogen is departing from this side, and this bond now becomes weaker and it gets broken. Once this bond between the carbon and halogen is broken, the carbon becomes a carbocation, and it goes from sp3 hybridized state to an sp2 hybridized state. So just observe what happens to the structure when the alkyl halide goes from an sp3 to an sp2 hybridized carbon. So I can immediately see that now the structure, which was like a tetrahedral because it was sp2 hybridized, has now become more like a planar molecule. So I can see that it's more like a planar molecule. Now let's consider a nucleophile. Let's say that it's a water. So let's consider water as the nucleophile, where the oxygen is colored in red and the two hydrogens are labeled as H4 and H5. Now, because this carbon, the C star, is sp2 hybridized, it is a it all the C star R1, the carbon that is connected to C star in the R1, R3, and R2 are all lying on a same plane. Now we can visualize this carbocation as a planar. So let's say that, for example, we can visualize this like a planar molecule with the carbon at the center and the three alkyl groups, one here, another here, and another here, right? So that's your planar carbon. Now, because this is a planar molecule, now the water molecule, which is acting as a nucleophile, can come on both the sides of the plane. So what do I mean by that is that this nucleophile can either attack this carbocation from this side, which is the same side as that of the, so which is on the opposite side, so which is on the opposite side, so which is on the opposite side to the departing bromine, or this nucleophile can also attack from the same side from where the bromine is departing. So this is from the same side from where the bromine is departing. Now, if it is attacking from the opposite side, then you will have inversion of configuration. So you will have inversion of configuration. But if it is attacking from the same side, you will have retention of configuration. Now, theoretically, one would expect that attack on either side. That is, so let's say this is your water. So it can attack from this side or from behind, and the probability is 50% and 50%. So you would expect that there would be 50% of inversion and 50% of retention. So ultimately this would give rise to a racemic mixture. So that's the expectation. But what one observes is that the retention of conflict, the ratio of inversion to retention is somewhere like 60 by 40 or something like 70 to 30. That is, you get more of inversion. So we get more of inversion. We get more of inversion. Now, the reason that is proposed for this observation is that it is the nucleophile, it is easier for the nucleophile to attack from the opposite side or to where the bromine is departing than from the same side as the bromine is departing, because bromine has not yet left this carbon completely. So it becomes difficult for the incoming nucleophile, in this case water, to approach the carbocation from the same side as the from where the bromine is leaving, and it becomes easier for the approaching nucleophile to attack from the opposite side from where the bromine is leaving. So that explains why we get more of inversion than retention, although theoretically one would expect a racemic mixture.